Hi class, and welcome to Unit 9.3 example problems. This is it. This is the last unit of the class. Congratulations if you've made it this far. I know this class is not easy. You've put in a ton of work, and I'm really proud of you. You've really done a great job this semester. Um, Now, this unit is a little bit unique, even more so than the first two. Um, if you recall, one of the prerequisites for this class is calculus, and this unit is the only reason why. This is the only part of this entire class where calculus is a basic understanding of calculus, integral calculus is required. And the integrals we do will be very simple. They will always just be simple polynomials, but technically there is calculus involved in this. I will ease your fears right now. You will not be required to know the calculus for the test. Any sort of problems that show up regarding moments of inertia or centroids on the test will be composite bodies, not these more complex curves where you have to solve using calculus. But let's jump into the calculus. So in the previous unit, we talked about finding the moment of inertia just using kind of some of our basic shape properties and knowing that we can combine composite bodies, add, subtract moments of inertia, do parallel axis shifts, and all that kind of stuff. Those relationships, though, for rectangles, circles, triangles, all that stuff, ultimately are derived from kind of the more basic equations um, and come from calculus. We can rederive those values using calculus. And so we're going to do some problems in this unit where we're given some funny looking shape with some curves, and we're going to be asked to um, find the moments of inertia using calculus. So this problem here, I am doing problem 10.3 and 10.4 in the book. It looks like this. So I've redrawn that here on the board. It's just sort of this goofy curve that goes up. Has the curve follows an equation of 4y equals x squared. And we're just given one that has, it goes 2 inches in, it's kind of capped off by this straight line that's 2 inches long, and the shape total is 1 inch tall. So the shape of interest is this shape here. And we're asked to find the ix and the iy, and these are about the x-axis and the y-axis. So how do we go about this? So what is the equation? So let's start with Ix. The basic equation that all of this is based off of is that the moment of inertia equals, it's an area integral of y squared times dA. And when we're approaching these, we're going to eventually end up splitting dA into well, let's talk about this. So what DA do we want to use? Um, by and large, it's always going to be easiest to use a DA who kind of runs parallel to the axis you're finding the moment of inertia about. So what I mean by that is if you look at our infinitesimal kind of cut, infinitesimal area, we'd want something that looks like this, that has a thickness dy, and its x length is just bound by whatever this line is. So if we were to rewrite dA with that understanding of this is my dA, this is my infinitesimal area, we can rewrite that like this, where we can say the integral, and we're going to integrate. So the integral from, let's see, so we get y squared, and then we're going to rewrite dA as, we're going to have to rewrite this equation in terms of x. So if we do that, we can rewrite that as x um, equals the square root of 4y. So we're going to plug in x, because that's our base of our infinitesimal area. 4y square root, I'm just going to represent it as a 1 power the 1/2, times dy. So this was dA. And we're going to integrate that, because now it's dy, we're going to integrate that from 0 to 1, right? So let's rewrite this. So we get ix then equals the integral from 0 to 1. And if we combine our y's, we end up getting 2 times y to the 5/2 dy. And when we take that integral, we end up getting ix equals, so you get y to the 7/2. See, 2 times 2 over 7, evaluated from 0 to 1, which gets us 4/7, which is equal to 0.5714 inches to the fourth. So that's how we would approach an IX. So right, again, we see units are of length to the fourth, which makes sense, right? Given what we had here, we have an area, which is going to have unit length squared, and a y squared, which is going to have length squared. So we should end up with length to the fourth. But again, when trying to figure out what dA to use, we want to use a cut that is parallel to the axis that we are trying to find the moment of inertia about. And the reason for that is when we do this, the reason this is nice is when we do it that way, the whole of the shape is at the same distance from the x-axis. If we were to do a cut this way, we could do it, but now the whole of the shape is not at the same distance from the x-axis, and we actually have to introduce the parallel axis shift into our equation. There's no reason to do it in basically any case. You can technically, but I'm not going to in this example, just because, again, you can always pick a smarter cut. So, however, now let's look at IY. Now for IY, we are going to want to pick a cut that looks like this. So now let's get rid of this cut that we used for the x, for IX. Now we're going to look at a shape that looks like this. This is now going to be our cut where it's going to have some dx, and it's at some x distance from our y-axis. So this is now our dA. So this equation is going to look very similar. It's going to be the integral, the area integral of x squared dA. And since this is our dA, we can rewrite that as the integral. We have x squared. Now we're going to end up with dx, and we need to figure out what this height is. Now this is where it's going to be a little bit different, because the height, it's not just simply, this equation x squared divided by 4. It's actually going to be 2 minus whatever this line is, right? Because we're bound by this upper line that's at a height of 1. So it's going to be 1 minus whatever this is, right? Because we need this height, right? So wherever this cut is happening as we integrate along the length, we need this height. So it's going to be 1 minus the equation of the curve. So x squared. And so that's going to be, so that y length is 1 minus x squared divided by 4 dx. And because we're going dx, so we're going to integrate kind of along this length. So it's going to be from 0 to 2. So let's kind of play with these numbers a little bit. So we get iy is equal to the integral from 0 to 2 x squared minus x to the 4th over 4 dx. So iy is going to equal to 1/3 x cubed minus, let's see, we get x to the 5th. So that's going to be 1/20th x to the 5th, evaluated from 0 to 2. And so that ends up giving us iy equals 1/3. So x, so 2 cubed is 8 minus 1/20th. 2 to the 5th is 32. So I get 8/3. And if we simplify 32 over 20, that's 8/5. Which if you do, some stuff with fractions, you end up getting that is 16 over 15. So iy is equal to 1.0667 inches to the 4th. So those would be our answers. And again, this should kind of make sense that iy should be bigger, right? The base, this overall distance that it goes, that ends up spanning from the y-axis is larger, is twice as large. So it kind of makes sense that, again, if I were to grab the y-axis and try to spin the shape about it, imagine the shape was hinged right here and I tried to spin it, it would resist me more than if I tried to grab the x-axis and rotate it. But at the end of the day, right, this is sort of the fundamental equation that our moments of inertia is based off of. So all those equations, if you really wanted, you could take a rectangle, apply this, do the integration, and you'd find that, the moment of inertia is 1/12 bh cubed, or if it's about its base, then it's 1/3 bh cubed, right? You could do all that kind of stuff, and you'd find that, hey, that's where it all came from. So hopefully that's helpful. Again, don't stress the calculus too much. If you need some help with the calculus, definitely reach out to me or go to the tutors or reach out to your study group. There are definitely people who are familiar and who can help you. So hopefully that's helpful. And again, as always, if you have questions or need help or just want to talk more about this, just reach out to me anytime. I'm always happy to talk. Thanks again.